Thank you everyone again for coming. I'm Hunter Kippen. I just recently defended my thesis, as they were saying, at the University of Maryland under my advisor, Dana Dachman-Soled. It feels so weird to actually like write the bio as having finished my PhD. I was so used to writing, oh, I'm a student. It's like, yeah. So that's fun. But I hope you enjoy the talk today. It's a pretty big collaboration that we've had with some people at Intel and with Maria at TNU. And without all of their hard work, this work wouldn't have gotten complete. So give them also your recognition. So am I clear to get started, or?
Yeah.
Oh, one thing, because of my setup, I won't be able to see the Zoom chat. So if you are asking questions during, would one of the organizers be able to read that out for me?
Yeah, sure.
Okay. Perfect. So then with that, I'll just get started. So the main motivation of this work, honestly, is that we're still having difficulties realizing large-scale deployments of FHE. So some of the challenges that we've had we're starting to really solve, right? So efficiency, we're getting there with some hardware projects, and some DARPA projects, other things. Usability is starting to get solved with better tooling. We've come a really long way on that. But like, there's still sort of one piece of this deployment puzzle that's been a little bit underexplored. And that's the risk involved with actually securing these deployments from a holistic perspective. So not just like, what about the security of the cryptography, but how do you manage keys? How are you separating concerns with who holds what keys? Rekeying policies, how many decryptions you might be able to release to certain people if you're using approximate FHE schemes, which is exactly kind of what this work is trying to see. And as I was saying, like, the concrete security efficiency trade-offs here are unclear. And in particular, when you're talking about CKKS, right, it's ring LW based FHE scheme introduced in 2017. And as most of you at this point probably know, if you're here, this scheme relaxes correctness requirements. So you're doing approximate operations, floating point arithmetic. Your parameters can be smaller because the noise growth in this scheme is much lower than that of BGB. And approximate arithmetic is sufficient for a lot of desirable FHE functionality, including but not limited to privacy-preserving machine learning. But again, this comes with some trade-offs, because there was, Li-Micciancio developed an attack back in 2021 on this scheme. So the idea is that the approximate correctness can actually lead to an efficient attack when you're composing CKKS into like a delegated computation scheme. So if you consider its decryption equation, you'll notice that that it just simply yields. This is neglecting the encoding and decoding scheme here, but the idea is basically that when you compute the decryption, you get a strict equation, a modular equation on your secret key. And if you collect enough of these, you have effectively enough to do a key recovery, or you can solve for S using these equations. With exact schemes, you have this rounding, and then you can't actually get these exact equations here. And the attack as originally specified is largely indifferent to CKKS's message encoding. So the countermeasures that were suggested for this scheme is to do something called noise flooding. So the idea is to add a significant amount of noise to your decryption. So in addition to just running your decryption equation, you sample some independent noise of your secret, and you add that before sending the decryption out to any user. And it turns out that in a follow-up work, they were able to analyze this noise flooding and using differential privacy that can actually prove security here. So there's a provable level of noise that you can use that will protect the decryptions in practice. Unfortunately, though, it's quite difficult to achieve high message precision with the secure noise flooding. So when you have the statistical parameter be only 2 to the 32, you can get single precision. But if you want, statistical parameter, statistical security higher than that, right, where you want 64 bits of statistical security or up to 80 bits of statistical security, you can end up with, only 16 or 8 bits of message precision left for your operations. And for many applications, that's not enough. And so then the question that we have with this work is, there's this gap, right, between there's actually a gap between the provably secure noise flooding and polynomial time attacks, right? So there's a level of noise flooding that you can have where there's not a proof, right? There's no statistical security there, but based on some of our analysis, it's not quite a polynomial time attack. And so then the question is, okay, can we analyze the concrete security loss that we would get from adding flooding noise in this sort of regime, and do this for various noise levels, different numbers of decryptions, and various types of circuits. And hopefully the idea would be to sort of find a balance between the amount of message precision that you can retain and the added noise that you have to maintain security. I want to preface, though, that with this work, we're trying to start the conversation on this. I don't think it's probably not a good idea to take this as the be all end all of like, oh yeah, if we use our recommendations here for your scheme or for your deployment, that you'll have 100% security. You still need to do this analysis yourself. The tools and techniques that we're developing here are good to start thinking about how to set policy, but additional analysis is definitely needed on an application by application basis. So then the question is, okay, how are we exactly doing this, finding this balance, right? So the idea is that we're taking a look at the framework of LW with site information. So we can model CKKS decryptions using this framework. The idea of the framework is that you insert sort of an intermediate step in the reduction from your LWE problem to the shortest vector problem, which you then, for attacking purposes, you would input into a lattice reduction algorithm like BKZ. This framework introduces an intermediate step. It's called the DBDD problem. The nice thing about this problem is that it's self-reducible. So if you have some side information, which we termed hints, you can reduce this problem to itself. This DBDD1 is an easier problem than the original DBDD problem, and you can do this for as many hints as you have, and then finally reduce your problem to SVP and run lattice reduction. And this is quite a nice framework for what we're trying to do because it allows for an iterative integration of side information. And so we can run and estimate lattice reduction on these reduced instances. For the original framework, there's 4 types of hints that were supported. In this particular work on CKKS, we're only focusing on 2 types of hints. So we have perfect hints, which we're mainly using for what we'll term guessing attacks later, and then approximate hints, which is how we're going to be modeling decryptions with noise flooding. So to give a kind of concrete example here, so let's again consider this decryption equation. So you have, your C0 plus your secret times C1. So these are the 2 components of your secret key or your ciphertext. And then you have your additional noise. So after rearranging some of this, you can actually, so you can get basically a linear equation on your secret key where you have this sort of big error term and your noise, right? Because your message might necessarily, like if you're the adversary can assume, and again, like in the Li-Micciancio style of text, the adversary may know the message, so they can get rid of that from the equation, and you'll just have effectively this noise here. But this is not an optimal way of doing these hints, because these hints are mod Q, and so you have this sort of approximate factor, and then also the modular reduction. And so you, at least in terms of this framework, it's not an optimal way to like think about how much information you can get from it. So in this work, we actually thought, okay, well, what about possibly a even stronger attacker model than the passive adversary that's considered by Li-Micciancio? So the attack model here is effectively, so we can think of it as having three parties. You'll have some kind of key store where the secret key is held. And then we have a user who knows the public key, and then an evaluator who also knows the evaluation key. Now you can think of the user and the evaluator as the same party in a lot of applications. But at least for the purposes of this illustration, the idea is, okay, so your user has a computation that they want to do, so they encrypt their message. They send, and note here that the user themselves is controlling the encryption. Right, so they have some ciphertext and circuit that they want to evaluate. They get the evaluation back, and then they can request decryption from somebody where they get the flooding noise added. And it's important here to realize that here the user themselves is effectively the attacker. They're the ones who control the encryption, and so they have access to internal parameters in the encryption. And so what that means is that if we again take a look at the decryption equation, we can dig a little bit deeper into this error term and expand it such that now we have a bunch of these attacker-controlled parameters, right? So the attacker controls the message, right, because they were the ones who did the initial encryption, and then all of these internal random values that were generated during the encryption process. And so you can rearrange this into a set of linear equations on the LW error E and the LW secret S. And then there's also, and as a result of this, there's no wraparound mod Q. And so we can actually get what's called an approximate hint from the framework, right? So it's an approximate linear equation on the concatenated vector ES. So you would treat the ring elements here as just their coefficients, and you would concatenate them. But there's some challenges with integrating hints in this way. So in FHE and in CKKS, right, dimensions are quite large. We have n up to 2 to the 17, right? So that's upwards of 120,000 or so. And just estimating the integration of thousands of or hundreds of hints is already sort of computationally feasible, right? The framework itself stores the covariance matrix of like the LW secret and error, and that would be, you know, effectively 200,000 by 200,000 dimensions. And then the precision requirements of actually maintaining sort of some of the geometry that we have to do for this framework is already a little bit of a problem. So we thought of a couple of different solutions. As a first kind of idea, we thought, okay, well, there's this idea of what's called full dimensional approximate hints in the framework, right? And it's a way of aggregating a system of approximate hints into a single sort of large hint that you can integrate all at once. But then the problem is that tracking this, like the covariance matrix or the ellipsoid from the DBDD problem requires this 2n by 2n matrix inversion. So instead of doing like matrix multiplications and whatever, which is already difficult, this now is even more computationally difficult. But we noted that we can actually calculate the remaining hardness. So like when you're talking about the actual hardness estimations that we get with the DBDD problem, it turns out that you can calculate the actual remaining hardness just with the ellipsoid volume. So the volume of this covariance matrix, since the lattice is sort of at this point fixed. And it depends on this, the matrix determinant of basically this hint system that you can create. And so, okay, so we can only calculate this volume and sort of neglect the idea of trying to actually run full attacks, end-to-end attacks, and just think about doing security estimation. But this explicit calculation is still a little bit too slow. So when we have, for example, n is 256, and we're only integrating 16 hints, calculating the determinant of this matrix takes roughly a week. Now this specifically, this is, hundreds or thousands of iterations to do, experimental validation. So this is like the duration of a single experiment, not just one of these calculations. But it's still not quite, it's still not coming anywhere close to approaching sort of the exact sort of dimensions that we need. So the idea is, well, instead, what if we tried to think of, like, because a lot of the statistical parameters are Gaussian, right? Or at least we can assume they are. A lot of these things are highly concentrated around their expectation. And so we thought, okay, what if we instead computed the expectation of the determinant of this matrix? And then if we can, given a number of hints and the distribution of those hints, then we can say, okay, well, the expected determinant of this hint matrix, and therefore then the final volume that you get in your DBDD ellipsoid, then lets you calculate the hardness of your final SVP problem, can be done analytically. And it turns out that we can do this. It's lemma 5.1 in the attached paper. It's a massive equation, and I did not, absolutely would not post that on a slide. It would be ridiculous. But we have a closed form expression for the actual volume of this resulting ellipsoid, and and the actual determinant itself was experimentally validated. So as I said before, there's this, like, when we're talking about doing 256 dimensional instances, so smaller toy instances with 16 hints integrated, we can show that the predicted determinant that we were having in this hint matrix and, like, the experimental determinant over time, like the actual expectation, matched very closely. And so this is all well and good, and we have sort of a baseline idea of how we want to run these sorts of attacks, right? So we have this analytical expression that lets us calculate the volume of effectively the final SVP lattice in expectation, given any number of hints that you would want to integrate from these fresh decryptions. And then we can get some hardness estimates from that. So, but then the question then becomes, right, okay, well, what about stuff beyond identity circuits? What about arbitrary circuits? How do we go from looking just at fresh decryptions to more complicated classes of circuits? Because that's really what people are going to be using in the real world. And so we consider two broad additional classes of circuits. We call them class 1 circuits. These are where you'll have sort of some number of leveled computations. So this will be some number of additions and multiplications. And then the final sort of level will be a bunch of multiplications with rescaling. And then these values are aggregated together as an addition. And then we also consider what we call class 2 circuits, which is effectively just two class 1 circuits then multiplied together. But the final multiplication is usually done without rescaling in these types of applications. And so we're saying, okay, let's consider this final multiplication without rescaling as just this kind of second class of circuits. And so the idea, so like multiplications can actually affect things quite a lot. So if you recall, in the identity circuit, we have this sort of all of these attacker controlled parameters, and we get an equation, effectively an approximate linear equation on the LW error E and the LW secret S. When you do multiplication with rescaling, it turns out that the rounding error so like the scale of the rounding error is actually dominant due to the scaling factor in CKKS. So the error that comes from multiplication and the error that comes from key switching is actually, because it's actually scaled by this rescaling parameter, the rounding error that you actually have is what dominates this sort of final error term. And so if you look at like the structure of this rounding error in each of these CI in this class 1 circuit, it's effectively some rounding error delta 1i times your LW secret S plus delta 0. The adversary can calculate this if they know the evaluation key. And so like that's where, you know, the attacker models will have to possibly change a little bit. But in most cases, the evaluation key is considered public. So that's just a minor detail. So given all of these, given the types of circuits that we were looking at, as well as so identity circuits, class 1 circuits, class 2 circuits, we ran an extensive number of experiments. So our main idea of the experimental setup is to do 3 different categories of noise flooding beyond the statistically secure noise flooding that was prescribed by Li-Micciancio. So here, when we're saying rho squared, it's the sort of average case estimate of the variance of your underlying noise in your ciphertext. So there was some work by Anna Maria Kosach and co-authors about basically how to measure the exact sort of precision loss that you have in CKKS, and you have this sort of average case estimate of the actual variance that's already present by just doing all of the multiplications and additions, whatever your circuit actually ends up being. And so we're taking this as your baseline parameter, because if you just choose rho squared as your actual noise flooding noise, then the amount of message precision that you end up losing is only a single bit, right? Because you're doubling the magnitude of your noise. And so that's quite useful. If that turns out to be sufficient for security, as we'll show in a little bit, that's probably not. It's probably not, and you shouldn't do that. And then we're thinking, okay, well, what if you just have a constant times this average case noise, and then scale the amount of noise by the number of hits that you're integrating. So those are like the number of decryptions that will get released. And we were able to validate a lot of these experiments by also running the same types of attacks for using the statistical noise flooding. And we were able to show that for all of these attacks, the statistical noise flooding holds, right? There is no reduction that we are observing in security when we use that. And we ran all of these attacks for parameters that were initially suggested by homomorphic encryption.org. So to give some sort of concrete numbers here, for lattice attacks, so these lattice reduction attacks, so here are the on fresh ciphertext. So that, again, this is, you have an identity circuit, you just decrypting what you get out of an identity circuit here. And so for example, for the smallest parameter set here, the way you want to interpret this this table is the original security is, so the security target on the left is the security target by the parameter scheme designers. And then on the right is the initial sort of security estimates that we were using our framework with these initial parameter sets. And then you'll have results for the 3 different types of noise flooding noise that we were using. And each of these were for 1,000 hints, right? So you were given 1,000 fresh decryptions with this magnitude of noise flooding noise. And sort of as expected, the more noise that you add, so if you scale the amount of noise by the number of hints that you're integrating, the more security you will end up preserving. And so, another type, so for some slightly larger parameters, if you compare, for example, the top line here, the larger the parameters get, the lower the security actually drops. And I'll get into a little bit of the why of this in a bit, but we can observe. So again, this is just for fresh ciphertexts. So what happens when we're talking about looking at the same type of attack for these class 1 and class 2 circuits? So I'm going to show a graph in a minute, but we have extensive tables that collate all of these results in the appendices in our work. But it's far too much to show here. So I just wanted to give you kind of an initial idea of what you can be looking at when you look at the paper. So with that said, sort of when you're looking at this actual lattice attack, so the way you want to interpret this graph is that we're looking at 128-bit and 192-bit target original security parameters. So, and this is on the x-axis is n. So instead of just, it's kind of hard to put all of the data points on as they are individually, right? So if you're looking at each of the parameter sets individually, it would be too difficult to kind of scatter. So this is how we were trying to do this. So the idea is that as n increases, the parameter sets will also change, right? So, but it's for the same sort of target security level. And then on the y-axis is the higher the number, the lower the security ends up getting. Right, so this is the reduction in bit security on the left. And as can be seen, for both target security levels, fresh ciphertexts exhibit the most reduction in security compared to class 1 and class 2 circuits. And this is to be somewhat expected, right? Because of all of the multiplications and additions that are going on in these more complicated circuits, you only get a certain limited amount of information, again, from this rounding error that you're able to observe. And so that reduces sort of the amount of information you get per decryption, at least in the case of running sort of lattice attack. But that's not the only type of attack that might be able to work on this type of setup. So we also consider it something that we refer to as guessing attacks. So the idea here is that instead of keeping track of the volume of the final lattice that you would get from SVP to estimate the hardness of running BKZ, the attacker could keep track of the LW secret and error covariance after T hints. So it turns out that if you do this, then when the variance is actually supposed to be small enough, so again, each hint that you get will reduce this covariance. And it's possible that you could, if this variance is small enough, right, where you're pretty sure that the secret and error is now the mean of your distribution, and the variance is small enough that you could round, then that's all you have to do, right? If the variance shows that with high confidence you're less than 1/2 off in all coordinate directions, then you can just round the mean. And so for a large enough number of hints, it turns out you can try and think about, okay, well, how can I guess maybe n out of the 2n coordinates, because then that's enough information for you to solve the LW system algebraically. And so for guessing attacks, we're looking at it in terms of the number of queries. So the number of ciphertexts or number of hints required to get to complete the amount of guesses. And here actually, because of the nature of the rounding error, where it's uniform between -1/2 and 1/2, it turns out that you need far fewer guesses to recover S compared to these fresh ciphertexts where you have larger variances initially because you're considering sort of the initial LW system. And so beyond just guessing attacks, though, we can think about a sort of a hybrid strategy. So maybe instead we want to say guess some number g less than n, right? Because we only need to solve for n of the coordinates in this guessing attack. And if we have enough high confidence coordinates, then we can integrate these guesses as what are referred to in hint framework as perfect hints. So they're exact linear equations on your secret key. And then from there, you can integrate, you can use a lattice reduction strategy from there. And so the hybrid attack, the trends from the hybrid attack kind of mirror that of the regular lattice reduction attack, right? Fresh ciphertexts, you'll see the largest reduction in bit security for fresh ciphertexts compared to class 1 and class 2 circuits. And so for some general observations here, we find that there's a greater reduction, again, in bit security for lattice attacks for identity circuits versus these class 1 and class 2 circuits. The hints that you get in identity circuits, right, so when you actually construct these equations, involve all 2 n coordinates in the LW secret and error. And that results in, but in class 1 and class 2 circuits, it only involves n coordinates, right? It's just the secret part. So only the variance of those n coordinates is reduced after each hint, compared to, at least in identity circuits, where you have all 2n. And that's quite important, and why we end up seeing the results that we're seeing. And then also what we found is that there's a greater security reduction for higher target security level versus lower target security level. So it turns out, like, when you fix the dimension, the higher the security level is, the smaller your initial LW modulus is. And as this modulus becomes smaller, the hints obtained from decryption have more of an impact on bit security for lattice reduction attacks. This is largely due to the fact that when Q, the modulus, is smaller, the initial volume of your lattice is also smaller. And so it takes less volume reduction to reduce the security. There's quite a bit of geometric things about that I do not want to get into, but I'm happy to answer those questions either offline or later. But yeah, the idea is that, like, what we observe when we're working with this framework is that the larger your initial lattice volume is from your parameter sets, the more work is required to actually reduce the volume by the same sort of amount to get the same kind of security reduction. So, and some other things is that what I showed before is that guessing attacks actually perform significantly better for class 1 and class 2 circuits. So for these more general circuits, hints can correspond to linear combinations of only the S variables. But for identity circuits, there's there's 2n total, like, eigenvalues when you're looking at, like, sort of this covariance matrix, right? You're trying to figure out how big it is in all dimensions. There's 2n eigenvalues that are reduced by obtaining hints, but n of those have a relatively much larger expectation. And so you end up with much looser bounds on the actual covariance, where you can't guess enough of the coordinates this way. But because, again, for, like, these class 1 and class 2 circuits, your error that you're looking at is sort of this rounding error, at least in terms of distribution of these equations. It's also much lower variance, and so you can the actual covariance matrix that you're looking at on the distribution of S is smaller. And we were able to validate sort of this absence of security drop when using statistically secure noise flooding. I would take a look again at some of the tables in the paper that show this. It's it's to be expected, right? But that leads lends credence to our confidence in the accuracy of our estimates. And what we found, obviously, also is, again, the biggest drop in bit security is observed when you do noise flooding by just sort of the noise that's already present in your ciphertext. So when you actually want to do noise flooding by the number of hints times this amount of noise, times the amount of error that's already present in your ciphertext, it can actually lead to a very low reduction in bit security in reality. And it's very possible that that seems to be enough, right? Again, I would scrutinize our tables and look at our equations, and for your application, I would make sure that that's what you want. But it seems to be mostly sufficient for these levels. Seem to be mostly sufficient for reasonable numbers of decryptions before you have to do any kind of rekeying. There's some things you can do that are a little bit less cautious, right? You could say, okay, multiply by some constant between 0 and 1 times the number of hints times this noise that's already present in your ciphertext, right? And so when I'm saying here rho squared, I'm saying like you have your circuit that you already know, and you have some estimate of the noise that's going to come out of your ciphertext after executing that circuit, and that's what you would set rho squared to. And so, perhaps for some higher dimensions, it's possible for some applications, right? A security loss of a few bits is acceptable. And hopefully the idea here is that, again, we can start to use some of these results to establish some key refreshing policies in large scale deployments, and to think about, these sorts of trade-offs and whether or not, for anyone's particular application, whether they're worth it or not. And so with that said, I want to say thanks everyone for listening to this, and I'm happy to take questions.